Hi, in this video we are going to analyze the Kruskal's minimum spanning tree algorithm and its time complexity. The heap data structure is used in the implementation of Kruskal's algorithm. So I have already made a video on heap operations and its time complexity. So I will highly recommend you to watch that video before watching this so that you will get a clear understanding of the Kruskal's algorithm. The outline of this lecture is going to be like this. First, we will see what is a minimum spanning tree, and then we will explain with an example the implementation of Kruskal's algorithm, and we will discuss the formal Kruskal's algorithm, and then we will do a complexity analysis of the Kruskal's algorithm. First, let us see what is a minimum spanning tree. So if you are given with a connected graph, the spanning tree of that graph is going to be a tree which connects all the vertices together and it will be the subgraph of the given graph. And we are already aware that if a graph has n vertices, then its spanning tree will definitely have n minus 1 edges. So if you have more than n minus 1 edges, it means that there is a cycle in that graph, and that graph will not be a tree. So what is a minimum spanning tree? A minimum spanning tree for a weighted, connected and directed graph is a spanning tree with a total weight less than that of other spanning trees. Kruskal's algorithm is one of the algorithms which are used to generate a minimum spanning tree of a given graph. It is a greedy approach based algorithm where every time it finds the optimum solution for the current scenario and add these solutions, and finally it will come up with the total solution. So here is an example of a Kruskal's algorithm working on a graph. So as you can see, the strategy of Kruskal's algorithm is to choose the minimum edge from the given graph and then continue this until you have n minus 1 edges. And while doing so, you should take care that there are no cycles. So now let us apply Kruskal's algorithm on this graph and identify how Kruskal's algorithm will generate the minimum spanning tree. So in this case, what Kruskal's algorithm will do is to identify the minimum cost edge from the set of all edges. So in our case, it is going to be this edge, which has got a cost of 1. And it is highlighted. So in the next stage, it will identify the next minimum edge. In this case, it is going to be 2. In the next stage, we can see that the next minimum edge is 3 and it will be chosen. And we can identify that there is an edge in the next minimum edge is actually 4. But if you join this, then it will create a cycle, and which is not advisable. So if it creates a cycle, then it is no longer a tree, and the definition of spanning tree will not hold here. So we cannot choose that edge. So the Kruskal's algorithm will not choose that edge, and it will run and to find the next minimum edge. So in this case, it is going to be 5. Now let me highlight the edges that we have chosen. The first edge that we have chosen was this, and then we chose this edge, and then we chose this edge, and then there was an edge which was going from here to here, but if we choose that, it will create a cycle, so we have not chosen that, and then we have chosen this edge. This edge. So this is the minimum spanning tree of this graph. So you can actually verify that this is the minimum spanning tree of this particular graph. The algorithm can be explained like this. The first thing that you need to do is to sort all the edges in non-decreasing order of their weight. So once you have sorted all of them like that, the minimum cost edge will be occurring in the first position. And then it will be easy for you to choose the minimum smallest edge. That is the smallest edge. So while choosing that, you should also check that whether it forms a cycle. So if it is not forming a cycle, add it to your solution. Otherwise, discard it. And then you have to continue this process again and again until you add n-1 edges to the solution. This is an informal way of representing the Kruskal's algorithm, where T is the solution set. You can see that T is initially a null set, which means that there are no solutions as of now. So the T will be getting filled as and when we add edges to the solution. So the condition here is that if T is having less than n-1 edges and our edge set is not null, then what you do is choose an edge VW from E of lowest cost and then delete VW from E, and if VW does not create a cycle in T, then add VW to T. Otherwise, discard VW. We can actually have a rough idea by looking into the pseudocode about the time complexity of this algorithm. Even though this is not a very formal algorithm, we can actually find the time complexity from this. So the first line is saying that this T is initialized to null, which does not take any time, which will be order of 1. And then this is the important loop here, which says that when T has less than n-1 edges. So don't mistake that this loop will run only n-1 times. This loop will, at the maximum run, we will have to go through all the edges. And if we are representing the edges as E, and the number of edges will be represented as modulus of E. So this particular statement will run E times, where E is the number of edges. And then what we are doing is that we are choosing an edge VW from E of lowest cost. Here is where we are making use of our heap implementation. So assuming that we have stored the edges to a min heap, then we know that the minimum edge will be present in the root itself. So obtaining that edge from that heap will take only order of 1 time. And then once you choose that edge, you also want to delete that edge from the heap. Once you delete this edge, then the property of the heap will be lost, and you have to perform the heapify operation. So the heapify operation is mentioned in one of our earlier videos, which I have indicated in the beginning of this presentation. So if you are unable to follow, you should definitely go and check the previous video. So deleting VW from edge set E is actually referring to the heapify operation. And we know that heapify operation will take log of E, because E is the number of nodes in our heap. And then there are 2 more statements written here, which says that if V does not create a cycle in T, and then add VW to our solution, otherwise discard VW. So these 2 lines are actually implemented in the formal algorithm using 2 functions. One is the find function and then the union. So once we learn about find and union, we can understand that find only takes an order of 1 and union takes again takes an order of log e, where e is the number of edges. So altogether you can actually calculate the complexity as you can see that one more important thing is that we said that we are choosing an edge VW. We are representing a heap. The edges are represented in the form of a heap. So first of all, we need to create that heap, and creating that heap actually will take you a complexity which will have a complexity of it will be in the order of e, because you need to create a heap with e edges. So totally, if you add all these things together, you'll be getting something like, you'll be getting something like order of e plus, I'll be writing only the significant things here, order of e plus you are executing this deletion and union operation e times. So it will be order of e into log of e. So this can be, this will be, the complexity of this will be only when in terms of big O notation it will be order of e into log e. So this will be the complexity of the Kruskal's algorithm, that is e into log e. So we will also analyze the formal Kruskal's algorithm, where also we can prove that it will be of the order of e log e. This is a formal representation of the Kruskal's algorithm. This is similar to the pseudocode that we have seen in the earlier slide. So let us analyze this. So looking at this algorithm, you can see that here again we have a while loop which says that where I is going, you have to iterate I up to less than n minus 1 and until heap is not empty. So this means that it will, in the maximum case, it will have to iterate this particular statement will execute e times, where e is the number of edges, which is represented by modulus of e. And then we are saying that delete the minimum cost edge uv from the heap. This again takes order of 1 complexity. Let me write this again. This line of code will take order of 1. And then reheapify using adjust. We know that reheapify will take order of log e. And then we are applying the find function. We are saying that find of u and find of v. And we already know that the find function is again will only take order of 1. We will discuss the details in the next slide. And once you made a find, you have applied find on u and v and derived j and k, then you check whether j is equal to k. If j is not equal to k, then only you will add this to our solution set. So that is what you can see here. If j is not equal to k, then you are going to add u and v to our solution set, and then we are also going to update the min cost as min cost is equal to min cost plus cost of uv. You can also see that a union operation is performed here on j and k. So we have indicated that this union operation again takes a time of log e. Here again, remember that we need to build the heap, and building the heap will take again order of e, since there are e number of edges in our heap. So finally, if you again sum all this up, then you can verify that this is going to be order of E log E. So it will be order of E log E. At this point, it may not be very clear to you about the details of the find function and the union function. So I will be covering find function and union function separately in a tutorial if it is required. I will just tell you some outline of what does find function and union will do to get a better understanding of the Kruskal algorithm as of now. So you are applying find function on u and v, which is the new edge that you have selected, and then you are getting two values as from which is from the find function will return you a value, that is find u is going to return you j and find v is going to return you k. And it means that if j is not equal to k, then it means that these vertices, selection of these vertices, that is u and v, will not create a cycle. If it turns out that j is equal to k, then it means that both u and v, the selection of u and v at this stage will create a cycle. So we are actually maintaining some sets where these vertices are kept. So it means that if u and v are already present in the same set, then j and k values will be the same. So if they are present in different sets, then j and k values will be different. You can also note that if j and k are different, then we are also applying a union of j and k, which means that which essentially means that when you perform find u and find v, you could understand that if j and k are different, it means that u and v are in separate sets. And now that you have a path, you are establishing a path from u to v, all the things in j and all the things in k are now connected. So instead of having two names, that is j and k, you are now going to combine j and k and then call it with a new name. Maybe you can choose j or you can choose k to name it. So it just means that you are combining two different sets into the same set, so that now all the vertices in j and all the vertices in k are now lying in the same set. If you are unable to follow what is find and union as of now, don't worry, we will be covering it in another tutorial if required. And just understand that the union is having a complexity of log e and find is having a complexity of order of 1. Thank you.